Well, now it's something to be seated. We are talking about fully in place functional programming, and the talk is given by Anton. Yes, please.
Yeah, thank you for that introduction. I think you can hear me, right? All right, thank you. Yeah, so I'm Anton Lorenzen. I'm at the University of Edinburgh, and this is joint work with my wonderful co-authors, so Daan at Microsoft Research, who's over there, and Wouter Swierstra from the University of Utrecht, who's joining us online. And this work is FP², fully in place functional programming. And this may sound like a bit of a contradiction at first, right? Because functional programming is all about persistence and immutable data structures. So how can things be mutated in place? And to illustrate this, let's look at the reverse function, how you would write it in a functional programming language. So this is in Coca. And if you do reverse, so down here you can see what the memory looks like. You get a list XS, which corresponds to the list 1, 2, 3. And we create an accumulator, which is empty. Then we push the first const cell onto this accumulator and do that recursively until we have the list 3, 2, 1 in memory for our accumulator. But kind of what happens under the hood is that really we have allocated a completely new list for the accumulator, and we still have the old list in memory. So maybe this is the last use of the list XS, and because of this will now be garbage collected, which is maybe a bit inefficient. So how would an imperative programmer write this? An imperative program would write something like this. So again, you have this list in memory, and you just have to consider what happens here. So let's kind of go through this code. We kind of, in a while loop, kind of keep on setting these pointers, and we kind of mutate the input list in place, where we just swap what the tail pointer points to. And so, in a way, we have achieved the same result, but in the memory, it's much more efficient because we have nothing to garbage collect and we have done no new allocation. And this is an example of an in-place algorithm because it mutates in place what its argument is. Now, what can we do in a functional programming language to get this? Well, in a way, maybe not so much, because we still want to have immutable data structures. So how can we change things if they should be immutable? But here comes a very nice insight from the paper Perseus, Garbage-Free Reference Counting with Reuse, which says, like, we can mutate things if we're the only one using it. Because if you're the only one who holds onto a piece of memory and you change it, no one else can see that you've changed it. So what the compiler does for you is that it kind of realizes if you write something like this reverse function, we have a const cell, XS here, that we don't use anymore, and we allocate a new const cell. So let's maybe try to reuse the old cell for the new. And it will insert for you this yellow block of code where it looks at the reference count of the cell XS. And if the reference count is 1, that means this list is unique. You're the only person who holds onto it right now. And then we can use the location of the cell to allocate the new cell in that place. Whereas if it turns out that the list is shared, so someone else can still use it and maybe depends on the data in that list cell, then we would have to adjust the reference count and allocate a new cell. Which means that in the case where we pass in unique data, this code will be just as fast as C. But if we pass in shared data, it's still like a functional program, it's still immutability. So you don't have to think about mutation when you reason about this program. However, as a programmer, if you write code like this, of course you want to make sure that this optimization fires, right? Because it's a very powerful optimization, and you really want to make sure that if you write a function, it's kind of in the right shape where this optimization can be done. And this Perseus paper describes this optimization really as in the backend of the compiler in the last step. So what we do in this paper is that we say we want to characterize when a function is in a shape where this optimization can take place. And we call such a function fully in place. And we have this nice keyword, FP, that is this abbreviation for it. And if you write FP in front of a function, the compiler will check for you that the optimization can happen. And if you pass in unique arguments, we will have no allocation, no deallocation, and the function uses constant stack space. And of course, if you pass in like a shared list or something, then you would have to allocate. And so this is a bit like a uniqueness type system, or like a linear type system that we saw also in the keynote in the morning, in that you can really now rely on this optimization. And what we do in this work is that we kind of create a syntactic check for checking this. So how would you do this? Well, we are building on this work by Martin Hoffman, type system for bounded space and functional in place update. And the idea is you have a linear calculus, so you can only use variables exactly once. And when you match on a const cell, you get not only the children, but you get kind of the space of the cell as well as a so-called reuse credit. And then if you want to look at this call, well, you can just use the variable xx once for that. And to allocate the new const cell, you'll now use this reuse credit to allocate it. So you're kind of thinking of like, where do I get space in forms of these reuse credits and where can I pass them on? And in our work, we can actually formalize this whole in a very small calculus. So in a way, this is a very simplistic calculus because it's a linear calculus, but we don't have linear types, and we also do not have closures. But we can formalize exactly the features that you need to express interesting algorithms. We have unboxing, and we have a simple borrowing system. So what this work really does is that we characterize the features you as a programmer need to write fully in place functional programs. And we also characterize this for a language designer. If you have a programming language and you want to support this, you can look at this calculus to see what kind of features you need. In the rest of my talk, I want to explain to you how cool this is and how many cool programs you can write in this style. And the first program I want to look at are splay trees. All right. So splay trees are one of these core computer science data structures. They were introduced in 1985 by Leijen and Tarjan, and they are self-adjusting binary search trees. And kind of the core idea behind a splay tree is that if you have a splay tree like this and you want to look up, you want to access an element, you have to move this element to the root of the tree. So that's kind of the description of the algorithm. So you can see here that we try to look up the third element, and once we're done, the third element should be at the root of the tree. And of course, if you implement this in a traditional functional programming language, that will be terribly inefficient, right? Because every time you look up, you'll have to reallocate the spine of this tree to kind of like, because you change kind of what the path from the root to the former element looks like. But actually what we can do in this style is that we can implement this lookup function without doing any allocations, as long as the splay tree you pass in is unique. So how would we do that? Now, let's define what a splay tree means in a functional language. That's very simple. A splay tree is either a leaf or it's a node with a left and right subtree, and the value is here an integer. And alongside with that, we'll define a zipper, which is either empty if it's the root, or otherwise it gives you the path down. So it's either node L if you want to go left, or node R if you go right. How does that look in practice? Let's say we want to go left inside a splay tree. We can write it like this in this function left. So you match on the tree, T, you're given. And if it's a node, you extract the left subtree L, and you create a node L zipper that contains the zipper you had previously, as well as the value and the right subtree of the current tree. And as you can see, this function is fully in place. Because if you pass in a unique splay tree, you can use the space of the node to allocate the zipper in that place. And of course, we return two things in a tuple, so maybe you were wondering that maybe we'd have to allocate the tuple, but actually if you have a language with unboxing, you can just kind of return multiple values at the same time without doing an allocation. And actually, you can also see in the code that this will be fully in place because we can annotate it with the FP keyword here. Now, this may seem like a new idea that you can write the left function fully in place, but actually, it is not that new because even in the original paper on zippers by Huet, there is this wonderful sentence, namely, efficient destructive algorithms on binary trees may be programmed with these completely applicative primitives, like the left function, which all use constant time since they all reduce to local pointer manipulation. Because this is really what is happening here. We take a node and we extract out the left subtree and put in the existing zipper. So we've just done a bit of pointer manipulation instead of doing like an expensive allocation operation. So let's look at how you would actually implement the lookup function in that case. We'll kind of go down the tree in some way and we'll turn this node into node L and node R's. So let's look at this in one example. So let's say I want to look up 3 in the splay tree I gave earlier. So I start with the root zipper. I've kind of at the root, I have nothing done yet. And I can see that 3 is of course smaller than 4, so I have to go left in the splay tree. And to do this, I'll replace the node I have by node L. And where the left subtree was, I now have a pointer to the zipper I had before, the root. And now 3 is bigger than 2, so I have to go right. And when I do this, I replace the node I had by node R zipper. And again, I replace the pointer of where the right subtree was by a pointer to the zipper I had. And then when I'm at the end, I'll call the Splay function, which will kind of unroll the zipper. But what you can see here really is that the zipper kind of presents the path that we took from the root down to our element in reverse. So this is kind of a pointer reversal technique, kind of similar to how the reverse function looked. Well, if we implement it like this, you'll see that this lookup function is not FP. We have not annotated it with the FP keyword, because there's a bit of a problem here. If we call Splay with just the left and right subtree into element 3, you can see that this node at the bottom is now unused. So we have a deallocation here, and we want to avoid this. Now, of course, we could modify our check to say, we allow this deallocation. But actually, this deallocation is a bit critical, because if you have a binary search tree and you just want to rebalance it a bit, you'll want to end up with the same number of nodes as you started with, right? So if we deallocate during this process, at some later point, we will have to allocate to end up with the same number of nodes again. And we'll see this if we now try to implement the Splay function from this point, that if we are at the root, if the zipper is just the root zipper, then we still need to allocate a node. So this is exactly the point where we'd have to do the allocation. So what can we do to write this function without any allocations at all? And the idea behind this is, again, we need to think about these reuse credits. What is the space we have available? In the lookup function, we had one node that was unused that we would have to deallocate. And now here we have a node that we would have to allocate. So maybe instead of doing that, we can thread through the reuse credit from the lookup function into the Splay function. We can do kind of a credit swap from the first function to the second. So if we write the lookup function now, and in the last step, when x equals y, and we call Splay, we now pass in some data structure as well. And this data structure will just be called top. It's isomorphic to a node. So you can see that it has just the right size to be reused against the node we have. And if we run through this example again, so we want to look up 3 in this Splay tree. We first go left, then we go right again until we're at the node. And now instead of just forgetting about this node, we will rewrite it to be a top and call Splay with this top and the zipper we have. And well, how do we actually now unroll the zipper and bring this element to the top? Now that's a slightly bigger algorithm, and yeah, sorry, it's that long, but it's also that long in the original paper by Sleater and Tarjan, and you can see we have these zig and zigzag transformations which just come directly from that paper. I mean, they did not use a functional language, but the algorithms come from there. But you can see that if we are at the empty root zipper, we can now reuse the top node for the node that we previously had to allocate. And you can see that actually this will work in all of these cases. You don't even have to look at them very precisely, because we have the FP keyword in the first line. So you just know it will be fully in place. And if I run this function, what will happen now is that I'll bring the top node to the top, and then in the case where now my zipper is the root, I'll just rewrite the top to a node. And I've ended up with the Splay tree where I've now correctly put the 3 node to the top, and I've done no allocation and deallocation. So that's one example for the kinds of algorithm you can implement with this system. I want to show you one more cool example. And this example is merge sort. If you want to write merge sort in a functional language, you see that it's often not fully in place. And the problem comes in the first step. So let's try to implement merge sort kind of the way it is traditionally implemented. The way this algorithm usually works is that you are given an unsorted list, like the list 4, 3, 2, 1 here. And then you want to, in the first step, create lots of singleton lists. So you'll wrap each of the list elements into its own list, with the invariant now that each of these singleton lists is obviously sorted because it contains just one element. And then I'll keep merging these sorted lists pairwise until I have just one big sorted list, which is then my result. But if I implement this algorithm like this, you can see that it is not fully in place. It will allocate, and there's really no way I could implement this precise algorithm without allocation. Because in the first step, I need to allocate all of these singleton lists, right? I have all of this extra memory that I need in the first step. But it turns out, by just changing the data structure a bit, you can change what this algorithm means. So we don't actually need a list of singleton lists in the first step. We just kind of need to keep an idea of where the partitions of this already sorted sublists are. So if we create a special data structure for this case, we can track that. And that's something that's what we do in the paper. So we create this partition data type, which is a list of non-empty sort of partitioned sublists. And the idea behind this is that we can now express the same algorithm, but in this new kind of format where no extra allocation is required in the first step. So if we have this list, 4321, and it corresponds in memory to a bunch of consoles, then what we do in the first step is that we rewrite it into a bunch of these one constructors of the partition data type. And as you can see very clearly, you can reuse all of the consoles for one of these one constructors. And at every step in this algorithm, we'll have exactly 4 of these constructors with 2 elements, which means we can reuse them against each other. In our paper, we have a bunch of algorithms like this. We show red-black tree insertion, where we use exactly the same algorithm as the Introductions to Algorithms book. We show quicksort, which is in place and also has constant stack usage, finger trees, and a map over any polynomial data type. And all of these algorithms don't have allocation, deallocation, and they have constant stack usage, as long as you pass in unique arguments. But of course, you will at some point need to create these unique arguments, right? FP kind of exists in a functional world. So how can you really reason about this in functional programming? Now, as I said, this is based on the Perseus reference counting optimization. So you can still use these functions even in a way where the argument is not unique. For example, you could write something like this palindrome function, where you take a list and you append it to its reverse, kind of creating a palindrome out of this list. Now, append and reverse are both fully in place functions. If you pass any unique thing, they can fully reuse that argument. But of course, it would be not sound for reverse to try to in-place update its argument xs here, because it will still be used for the call to append. Now, in a reference counted system, that is no problem, because as you can see, I have 2 uses of xs, and so the reference count will not be 1, and no in-place update will happen. But how can we really reason about this? And our idea here is that we add 2 new rules to our calculus. We have one contraction rule that allows you to use something that you already have twice, and we have a weakening rule that allows you to forget about something. So as you know from linear logic, these are exactly the 2 rules that kind of add nonlinearity to your language. Now, it would not be good to add these just to the fully in-place calculus, because once you have forgotten about the linearity, there's no way you can do the in-place updates in general. But these rules actually make a lot of sense in a reference counted system, because using something twice, you can just represent by reference count increment. So the stub function will increment the reference count at runtime. And forgetting about something corresponds to reference count decrement, where the drop function will decrement the reference count at runtime. And so what we do in the last part of our paper is that we take this fully in place calculus, and we add a bunch of rules for nonlinearity and closures that you can implement by reference counting. And what we get is a new view on the Perseus algorithm. So we can see in this way Perseus as a linear calculus for correctly placed reference counting instructions. But also, we have a new insight into FP, because we can see that if you are in a Perseus-style reference counting system, FP is kind of the fragment of the language that can be executed without any reference counting overhead. You don't have to increment and decrement the reference counts as long as you're in the FP fragment. The only overhead you have due to reference counting is by checking every now and then whether you still have unique data. And that is something we also see in our benchmarks. So in our benchmarks, we compare FP, this is in red, our fully in place functional programs we propose in this paper, against the standard implementations that you would have in a textbook like Okazaki. So we have standard reuse, that is in yellow, and this is the version of the like typical functional algorithms that where we apply reuse analysis, and we also have standard where we do not apply reuse analysis. So you can kind of see across the board that reuse analysis helps quite a lot for these algorithms. And when possible, we also compare against C and C++. I only want to talk about one benchmark here in particular, and that is the TMAP benchmark. The TMAP benchmark maps over a shared binary search tree. which means that in this benchmark, reuse analysis actually does not work because the tree is shared, so there's no opportunity for reuse. And you can see that in this case, actually the standard reuse program is a bit slower than the standard program because attempting to do reuse analysis has a small cost. But as you can see, it is very small, like the cost is very small. So even if if the reuse analysis actually does not succeed, it's still not that bad for performance. Whereas in the other programs, the reuse analysis can succeed, and their reuse analysis is very good. But we can also see that the FP program we have is quite a bit slower than the standard program. Now, this is really because these are two different implementations. The standard program recurses on the stack, which means that if you have a very unbalanced binary tree and you map over it, you can run out of stack space. The FP program, however, is required not to run out of stack, right? This is our guarantee that you have constant stack usage. So we allocate a zipper, pretty similar to how we implemented the Splay tree example, to make sure we don't do this. But then, of course, we have to manage the zipper, and that has a bit of overhead. But, of course, what we get is a good bound on stack usage. Thank you very much for listening to this talk. I hope you liked it. We have... Thank you. So before I take questions, I quickly wanted to say we have fully implemented this in the Coca language. You can go online and download it. But also, you can visit the demo at the Microsoft booth at 13:30 today. And we're very happy to take further questions there and show off our system.
Well, thank you. And questions? Javor, please give your name.
This is Javor Diachki from Gallo. So when I've seen this kind of in other languages like Rust or work on mutable value semantics, they usually annotate the arguments of a function to kind of indicate ownership type or something like that. While here you chose to annotate the whole function as somehow being in place. So I was kind of wondering if you could comment a bit on this choice, because I could imagine some things are being updated in place and others not. So how does that map to the whole function being in place?
That is a good question. So we don't show it in this presentation, but we also have small annotations on function parameters. We can say a certain parameter will be borrowed. That means you will not try to, for example, return it, and you will not try to in place reuse it. So it's kind of like a read-only value that you can borrow for the duration of the function. Yes. Yeah, I'd have to think a bit. So it would certainly be possible to annotate the function parameters for, like, this is something that should be used linearly. Yeah, I'd have to think a bit like what the trade-off there is.
Yeah, like have a look. They have in Swift some work, and they have in-out parameters, they call them, and it's very similar to this. Very cool work. Thank you.
Thank you.
Simon.
Simon Peyton-Jones, Epic Games. I've got a similar question that's to do with fragility. Suppose you've got a function. Actually, your Splay was a kind of example in which many paths, a lot of the function is FP, right? But then there's just one little corner, perhaps even on a cold path, that's non-FP. So it seems to be a bit all or nothing. Really, you'd like to say, look, get all the juice you can, and if there's a little corner with no juice, well, allocate.
Right.
Have you found that in practice? I'm just worried whether, in practice, it might feel a bit fragile to programmers. They make a small change and boom, they don't get anything FP.
Right. So the reuse analysis that is implemented in the backend will always try to reuse as much as it can. So that is kind of independent of this FP work. The FP work just kind of gives you a view on when it will succeed, but it can also succeed if the FP check kind of fails. So you will not see any difference in performance due to that. I agree, though, that it's usually useful for a function to be able to do, for example, a small amount of allocation. You see this a lot with something like an insertion function, where you do want to reuse all of the elements of the tree, but then when you're at the bottom, you need to insert a new thing, right? And actually, we also do that in the paper. So we have, in Coca, you can write like a FP keyword with a small 1 behind it. That means you can do, this function is fully in place, but it can do one allocation. And that you can then exactly use to type something like the insertion function.
Okay, thank you.
So let me interpose an online question. I think it's relayed by Edwin Turek. Can we express Linux RCU-like data structure of the operations in FP, or can we implement a single writer multi-reader concurrent data structure in FP?
I'm not an expert on concurrent data structures, so it will be hard for me to answer that question. Yeah, I think I need to look at a precise example. But yeah, we can do a lot of data structures in this, so I think there's a good chance it could work.
Yeah, that's fair. You could discuss it on the...
Yeah, I'll discuss it.
Please.
Hi, Sam Westrick from Carnegie Mellon. Really fantastic talk. I'm really excited about this work. My first impression is that it's integrates well with sequential programming. And maybe this is maybe a simpler version of Edwin's online question. Can you speculate a little bit about integrating this into a parallel system? But let's imagine like something simple, like purely functional parallel. What are the challenges of integrating FP into such a system?
That is a good question. I mean, the whole idea of FP is that you mutate things when they are unique. So I'm not really sure what the relationship is to parallelism in the sense that if something is unique, you know it will be only on this thread, right? Because there's no other thread that can hold on to this. So
yeah, maybe the challenge is just figuring out uniqueness, perhaps.
Right.
Yeah, good. Thank you. Yeah, this is really great. Thanks.
Hi, Alexei Radl, Google. My question is about memory fragmentation. So my question is about memory fragmentation. If you program in a FP style, then wherever the nodes got allocated when you first allocate them, there they stay forever.
Right.
But I might imagine that a data structure like a Splay tree, if you access it many times without allocating anything else, will tend to compact the top elements into one region in memory so that then they're in the cache all the time when you're accessing them. Have you found functional in place to have positive or negative effects on caches?
Yeah, right. It certainly changes where things are placed in memory. I think there are probably examples where it does badly and places where it does well. So, for example, with the Splay tree, you can, like, if you, let's say you're in a traditional functional programming language and you allocate like a big Splay tree in memory, and then you look up quite a few times. Then every time you look up, you have to reallocate the spine of the tree. So you have like your big Splay tree in memory here, then like you get all of the splines somewhere else. Whereas if you do all of this in place, kind of because kind of you only change things inside this big data structure, you stay memory-wise inside this big blob where you once allocated it. So that's one case where I could imagine that it does a bit better. Right. Otherwise, you can also ask Daan about this. He's kind of an expert on memory fragmentation and memory allocators, so I'm sure he'll have a good answer to that.
Okay, so you haven't like studied what actually happens in practice?
Yeah, let's maybe get the two remaining questions and maybe take it offline. Yeah.
Jasper Gear, Tufts University. I was wondering if there's any kind of notion of like a policy for reuse in the case that maybe I have multiple space credits that I might use if I'm operating on a really large data structure, but I also have kind of a smaller accumulator, I might want to reuse the accumulator's memory for the accumulator to maybe maximize like temporal locality. I was wondering if you've explored that.
I mean, we always reuse the zipper against the, like we reuse the original tree against the zipper and then the zipper for the new result. Was that your question?
I think this was more on the level of the system itself, maybe not like on the authors, the function authors side, the actual the compiler.
Right, how the compiler could exploit this. Yeah, I think that takes too long to answer.
Yeah.
I'm very happy to answer that. I'll come back later to you.
Maybe we could take that offline. Do you have a short question?
Really short.
Last one anyway.
If the user writes, May Milano, Princeton University, if the user writes a program that they annotate as FP, but it turns out to have a reuse, what's the experience of getting an error like, and does it guide you towards understanding how to make it FP?
So you mean when you annotate a function as FP, which is not FP?
Right.
So there's an error.
What does the error look like, and does it help you make it FP?
So we have implemented this in the front end of the compiler. So the check is on kind of the source language. And then what the check does, it kind of tracks these reuse credits, and it says you, hey, this is the code path where I maybe did not have enough reuse credit, or I had too many. Maybe you want to fix that. So
Well, let's thank Anton again.